Hello mates, lovely day for our lovely master class. Yeah, if I do say so myself. Okay, last time we started talking about how linear systems of differential equations are represented in some sort of nice compact matrix form. Okay, and we started discussing and trying to understand their important properties. Okay, let's just make a short recap and look at some sort of example, so things are clear for some of you who are probably not very familiar with this type of thinking. Okay, so assume you've got this very simple system of the gravitational pendulum. That's a ball of mass m connected to some sort of beam or rigid rod of length L, okay, swinging with an angular displacement, if we can say so, theta, okay. And we want to model the evolution of such a pendulum, okay, the evolution of its position and as well as the evolution of its velocity. Okay, well, I won't go too much into the physics of the details. Okay, usually the body is subject, since it's a gravitational pendulum, to the gravitational force. Okay, and also since it's swinging back and forth, it's somewhat connected to some or it's stopped, okay, by some sort of friction force or damping force. Okay, now if you do all the physics about it and look at the tangential component, that's, if you remember some of the basics in physics, you'll find out that the pendulum is governed by a nonlinear equation of this type: ml theta double dot plus mgl sine theta, okay, and the sign says it all, plus k theta dot. Okay, let's first assume that you've got no external influence, is equal to 0. Okay, now we are talking k theta dot L, sorry, because we are talking in torques. These are no longer forces because it's about rotation, a movement of rotation. So essentially these are torques and not forces. Okay, this is usually the inertia in movement of rotation. Okay, and this is given by the tangential component of the gravitational force. Okay, so if we divide the entire equation by ml squared, the pendulum will be governed by this second order differential nonlinear differential equation. Theta double dot is minus g over L sine theta minus k over m theta dot. Okay, so this is the of course here we have to assume some theta 0 non-zero, as well as theta dot 0 is non-zero. So some sort of initial position of an initial angle and an initial velocity which are non-zero, because otherwise the pendulum is doing nothing. It's just hanging. Okay, these are the initial conditions. Okay, so theta is the angle, theta dot. So theta, no, sorry, theta. Theta is the angular position or displacement. Okay, and theta dot is the angular velocity. Okay, it's the angular velocity. Fine. So now we are trying to model this system as a first order a system of first order differential equations, because we do not deal with second or higher order differential equations unless we know how to turn them into first order equations. So this is very simple. We have done that before. So you just call the state variables x1 is theta, which means that the second state variable is x1 dot is theta dot is x2. So these are state variables, okay? I remind you, state variables, okay? Which means that this equation is equivalent to a system of two equations. X1 dot is x2, and x2 dot is minus g over L sine x1 minus k x2. Okay? And this can be written in compact form. This can be written in compact form. So now we call x, which is the state vector, we call x to be the vector x1, x2. This is in R2, so it's in the plane. Okay, it's in the plane. So we can easily write that x dot is x2, and here we have minus g over L sine x1 minus k x2. Okay, we can have that, and we can call this fx, and this is a nonlinear system. But we do not do nonlinear systems here for the time being, so we need a linear model. Okay, so we compute the equilibrium points, okay, or the stationary points of this system. That means x dot is 0 when there is no dynamics, when everything is in steady state, okay? When everything is still static, non-dynamic. So that means that x2 is 0 and sine x1 is 0, okay? Which is equivalent to the fact that x1 is of the form kp, kpi actually, true, and x2 is 0, k is an integer, okay? These are the equilibrium points. These are the equilibrium points. Okay, let's take k equal to 0. Okay, so for k equal to 0, we have here two types of equilibria. Okay, we have here two types of equilibria. We have this equilibrium, and we also have this equilibrium. Okay, so this is 2k pi. This is the even numbers, and this is 2k plus 1 pi, the odd numbers, okay? Now, to get the linear system, we need to check the infinitesimal movement of this pendulum, okay, around the equilibrium point, in the neighborhood of the equilibrium point, okay? So we select peak, okay? The equilibrium point x star equals 0, 0. So that's when the pendulum is stopped. This is 0, 0. Okay. This is 0, 0. Okay. 0 velocity, 0 angle. Okay. And linearize. Now, because I do not want to get into details, what do we usually do when we have such a nonlinear function and we need to linearize? What do we do?
We apply some transformations.
Okay, fine. Forget about that. Let's make it simple. What did you do in physics when you knew that for very small variations?
Taylor series.
Exactly. For very small variations, sine x1 is almost x1. Okay? In this case, so we get, so we do linearization, linearize, okay? In this case, let's use a new variable. Let's use what? Z, okay? In the new variable, z dot is z2 minus z2. No, sorry, plus z2. I don't know why minus. So z2, x2 is z2. And here you'll get, in the second equation, you'll get minus g over L x1 minus k x2. And this is a linear. This is linear now. Okay. Okay, if this is linear, then we can write this as az plus, as az because we didn't use u. We weren't using u. We can add it later. Okay, az. Okay, so what is az? What is az? So we can write it as a times z1, z2. So this is what? 0, 1 minus g over L minus k times z1, z2. But I think here is minus k over m. Sorry. And here too, I think. Okay? Okay? Of course, you can always add the input term in the second equation. So we can always say 0, 1 times u. U is a scalar signal, okay? So now you get a z plus b u. And you can also pick, this is a selection you make, you can pick an output. The output, pick the output. Pick the output, okay? Y equals what? What do we want to measure? Angle, velocity, or both? What should we use?
Both of them.
Both of them. So you wanted multiple input, a single input, multiple output. Fine. So y equals z. z1, z2. So its identity, we can write it like this, times, this is the identity matrix, okay? Times z. Fine. So now you get the linear system, x dot. We can go back to the x, okay? Because we are used to it, ax plus bu, and y is x. So c is the identity, okay? So this system now is defined by the matrices A, B, and C, okay? Is defined by the matrices A, B, and the identity in this case, okay? But it can also be defined by a transfer function. By a transfer function, okay? So it has the transfer function, which is the quotient y when you go to the Laplace, okay? Y of s over u of s. This is a matrix, okay? So this is H1 S and H2 S, okay? And this can be computed as C, as we saw last time, is this one, okay? So these objects represent the same thing. The only problem we need to study is, okay, so this object is second order, okay, because it's always the dimension of matrix A, okay? So second order system. And this is also a second order transfer matrix, okay? It's a second order transfer matrix. So the question is now, for instance, in model reduction, how to approximate this with a first order transfer matrix. A simple transfer matrix, okay? Did I make myself clear why we study these objects and how we want to approximate them? Okay, so idea of model order reduction. Approximate linearized, approximate the linearized pendulum with first order transfer function, okay? Okay, because this is a second order transfer matrix in the sense that the denominator of this transfer matrix, so this is always can be written as an RS polynomial over PS, okay? This is a polynomial with matrix coefficients, whereas this is a classic polynomial, okay? So the degree of P is 2. The degree of P is 2, okay? So the order of the transfer matrix is the same with the order of this object, ABC guy. Is this clear to you?
Yes, it is.
Okay, fine. So model reduction. So in model reduction, you get ABC, which is equivalent to the transfer matrix of order n, okay? And you want to approximate this with a lower dimensional system. You want to approximate this with a lower dimensional system, okay? Let's try to do something in MATLAB so you get some sort of refreshment. I'm going to refresh your memories of MATLAB. If this is something you'd be interested in. Otherwise, we can proceed with the lecture. So. Can you see my MATLAB screen?
Yes.
Yes.
Okay. So this is the pendulum. For instance, in the nonlinear case, because this is a very small system, we can numerically integrate the system. So we can explicitly write the differential equations, as you can see them here. Okay. These are the differential equations. This is the pendulum. Do you recognize it? Okay. This is the pendulum. And okay. Here we've got the mass of the pendulum, which is 20. The length of the rod or the beam, which is 10. Maybe this is a bit too much. And the gravitational constant, which is 9.8. And we also have a friction coefficient of 0.05. Okay? And these are the equations we have just written. Now, you can imagine that for the building or the CD player or the card pendulum I just showed you, this is not feasible. You cannot write the equations in this form explicitly. Is it obvious? I think it makes sense, huh? We cannot write hundreds or thousands or tens of thousands or millions or billions of equations in this form. Right? So, but in this case, this is simple. And now we can numerically integrate these equations. We can use the ODE functions of MATLAB. This is the MATLAB function, which performs numerical integration of a differential equation for both equations. And we can look at some plots. And this is what we're going to do. Okay, so here we compute. This is how the pendulum is swinging. You see, the pendulum is swinging. Note that the friction is very, very small. Okay, the friction is the pendulum is swinging for a long time. In the second figure here, we have the phase plot showing the trajectory in the plane of the display of the speed of the velocity versus the displacement. You see, velocity versus position or displacement. Of course, that if I increase the friction, here, so let's make it 0.5, so 10 times. Okay. You can imagine things are going to change. You see, you can see that slowly they're going to stop. It's going to stop. And essentially, it will go back to the stable equilibrium point. It will go back to the stable equilibrium point. Let's double this, or make it 4 times even. Okay. Now you plot this. You see, the movement is fading. Yeah, the movement is fading. You see, and it's going towards 0. So this is the real behavior of the nonlinear pendulum. Now let's look at the linearized pendulum. Okay, so here we won't have sine. We remove the sine. Okay. Let's check here the initial conditions. So there are small variations. Okay, you can see that. Okay. So for the linear system, we do this. Okay, I think we should close the figures first. Yeah, you can see that the behavior is pretty much the same. So it makes sense to study the linear systems around the equilibrium points of a nonlinear phenomenon. Okay, and then perform what we are doing in this lecture. Then do what we do in this lecture with the final scope of performing simulation, stability analysis, other property analysis, as well as control design, because this is the final goal to be able to perform. I don't think I forgot to mention in the beginning of this lecture that control design is suffering from the so-called curse of dimensionality. I'm not sure whether you've heard about it or not before. Curse of dimensionality means that the dimension of the controller usually is equal or larger to than the dimension of the plant to be controlled. Okay, so this is an issue. This is another reason why we need model reduction. Okay, we need model reduction to have low dimension approximating models to be able to perform control design. Okay, and of course, finally, you need to validate the controller on the original plant. Okay, so this is the linear integration of the system. However, this linear integration of the system is not what we want to do. We want to work with 4 matrices A, B, C. So what we need to do is we need to build the matrices. Okay, so A is 0, 1. It's oh, so no, I'm going to make another script. I think it's easier to perform another script. Do you agree?
Yes.
Okay, let's make another script. Let's close the figures first of all, because I do not need them at the moment. So because I need, what do I need now? I need these coefficients. Okay, so Control C, new script, Control V. Okay, so now I'm building the matrices. A equals 0, 1, no, 0 space 1. This is, do you know how to introduce a matrix in MATLAB? You're familiar with that, right? Minus G over L minus K over M. And this is your A matrix. Your B matrix. Now we make some input for the system. Let's make it 0. 0, 1. It's a column. Okay. Well, actually, I want to do this. A, B. Let's make C is the identity. I. That's how you introduce the identity matrix in MATLAB. This is I2. Okay. And now your pendulum, or linearized pendulum, let's call him LP. Okay. Is state space. Now, MATLAB is building up an object called state space, A, B, C, and he also needs a zero matrix. A zero matrix. The zero matrix is always a matrix which has the size is given by the number of outputs times the number of inputs. So we have two outputs, displacement and velocity, and one input, okay, which is going to be some sort of torque. So this is going to be zeros, 2 lines and 1 column. Okay, so let's try to run this. Let's save it somewhere. I need to save it in my files somewhere. Okay. Linearized. No, not here. I don't need it here. I want to put it in your course, in your lecture. So here, simulations. Okay. Simulations. Linear pendulum. Okay. It's going to be an M file. We add this to the path and we run it. Okay. And now this guy is going to build us, you see, is going to build us the system. Okay, so look, this is the output. Okay, this is the input B, and this is the dynamics. Okay, this is the dynamics. Now let's try to simulate once again. Okay, the previous. We want to perform the simulations we did before. In the previous simulation, we did not have an input, but the initial conditions can also be an input, some sort of impulse input. It's an impulse input. Okay, so we are going to make impulse of cis. Okay, what happens? Not cis. I said LP. Sorry about that. Impulse LP. Let's see what happens. Look, you see? Displacement and velocity. Okay? So we get the same pictures we did using numerical integration. Okay? But this guy is now computing what we are going to call the evolutions, or we saw last time, if you remember. This is the free evolution. This is the free evolution of the pendulum, okay? Because it's an impulse response, okay? The response to initial conditions is similar to an impulse response. I showed you last time, okay? Of course, it's a convolution system and so on and so forth, but this is an impulse response, okay? Now, let's build the transfer matrix. So now we call H is equal, no. We have to build, because the nominator R and the denominator P is state space to transfer function, if you remember this function, of LP, okay, but this is not necessarily all right. No, I think we should just use, let's see if we can do this. H is transfer function of A, B, C, and zeros 2 times 1. I cannot show you right now the transfer function. I don't know why. Let's do help SS to TF. Let's see what the help has to say. Okay. So num then calculates the transfer function of the system. Oh, so this one is computing the transfer function for each input. For each input. Okay. So we should have indicated the input. But we have the same input. They should have indicated the output actually this time. Help T. Oh, this is much more. Oh, so we need TF nominator and denominator. Okay, nominator and denominator. Okay, never mind. So the idea is, you see, it's difficult to work with transfer matrices. It's easier to discuss state space system for MATLAB, because MATLAB knows matrices. Okay, MATLAB knows matrices. So we've got this this second order model. Okay, all right. So now it's interesting to see if we can substitute this with the first order model. Okay. So what does this mean? What does this mean? We can build now A equals, say, minus 0.5. Okay. B is 1. B cannot change too much. Okay. And C is the same. C now is also only 1. No, we should have again 2 outputs. Okay, so C now has to change somehow. Let's take only one output. Okay, let's take only one output. Let's say also C equal to 1. Okay, and now we have LP approximated. Its state space of A, B, C, and 0, because we don't have no feed through term. Okay, and now let's do again impulse of A, B, impulse of LPA. Happens. Where's my figure? Okay, so now you see you only have one approximating value that in the steady state, you see, has the same behavior. Steady state is after a specific time. Okay, you do not see the oscillations any longer. Okay, but you can see here that in the steady state, it's also going to 0, just like the original model. Okay, so this is only one variable which needs to capture both the displacement and the velocity of the pendulum. Okay, of course, this is from the top of my head, ABC. We need to systematically compute ABC to capture both behaviors. Okay, probably B and C should be much smaller. Okay, so B and C should be much smaller, so we can get some oscillating behavior. Okay, something like that. Okay, now it's just pure intuition. This is just pure intuition. This is no systematic thinking. Okay, no ordered behavior. Okay, something like that. Okay. Did you guys do you mates understand what I wanted to say with this example? So I showed you what people usually do. They start from the nonlinear phenomenon, they do a model somehow, They linearize. They usually like to get a linear model, and then we come afterwards and perform approximation on the model. Is this clear to you?
Just clear.
Okay.
Yes.
Fine. So for this reason, we need to study the systems defined by these matrices A, B, C, and D. That's why we started discussing last time about these models. Okay? I have different models here. I also have something related to the COVID spread, which is 4 equations. These are also nonlinear, and they can be integrated. Okay? This is kind of interesting to watch. This is a very simple model written by some guys. I'm going to run it for you just to give you an idea. So this is a COVID model, COVID spreading model without any control whatsoever. Okay. So essentially, the equilibrium is like this: everyone is dead, no one is any longer exposed, no one is any longer infected, no one is any longer susceptible. Okay. But removed is everyone, because this is the entire population here, okay? So essentially, the model is really stable, but we do not like that, because stability in this case means that if nothing is done, everyone is going to die. I'm sorry about that. This is how this model looks like, okay? This is also quite interesting, and interesting to approximate as well, and capture its interesting behavior. Okay. So let's go back to our slides. I'm going to close this share screen and go back to the share screen of the lectures. Okay. Okay, let's go back to Teams, share screen, start sharing. Okay, so like I said, I was trying to give you an idea why we do study these quantities with A, B, C. Why isn't this opening? Okay. I'm restarting the iPad. Can you see my screen?
No.
No. Now you can see it.
Yes.
Assembly. Okay, we're back to our slides. So as you've noticed, we can easily so we have this object A, B, C, D. We can also have the transfer matrix. There is also a relation which we are going to discuss between the ABC matrices and the TS. It's a close relation, and we need to understand this relation between TS and the matrices A, B, C, D using this notation here. Okay. So this is the transfer matrix. Okay. This is a transfer matrix associated to the dynamical system given by matrices A, B, C, D. Okay. One interesting property of this ABCD, guys, is that you can always change the matrices ABCD using a so-called coordinate transformation and not change the significance of your system. This is very, very important to us, because we'll see that one of the model reduction techniques relies on this property of equivalence of linear systems. Okay? So usually, where does this come from? Usually, when we have a matrix A, when we have a matrix A, a square matrix A, okay, this square matrix has associated a spectrum of eigenvalues. Okay, I'm just going to write like in MATLAB, A. Okay, these are the eigenvalues of A. However, these eigenvalues and other properties of the matrix do not change. Do not change. So you can always multiply this matrix with an invertible matrix in this form, and you get another matrix A, okay, but having the same set of eigenvalues. They do not change. Okay, they do not change. These are called coordinate transformations. These are called coordinate transformations. So you have a system which is x dot is ax plus bu, and you do not like the x and the shape. You do not like the shape of the matrices A, B, and even C. You do not like the shape of these matrices. Okay? You want the matrices to emphasize your dynamics in a different fashion. In a different fashion. Okay, so then if you want to do that, then you make a coordinate transformation. You multiply x with a T matrix, and then you get a new vector z. Okay, so x is Rn, T is Rn times n, then z from matrix multiplication is also Rn. Okay, so the dimension of z is not changed. Okay, it's not changed. Now, if you take the time derivative, then you get T is a constant matrix. If you take the time derivative, this is T x dot. True? This equals Z dot. True? But Tx dot is, from this relation here, is T times Ax plus Bu. Do you agree? Okay. Then this is Tax plus Tbu. Can you write x like z? So z is Tx. Okay, T is invertible. Then who's x? Who is x?
Inversor of T
Inverse
multiplied with Z.
Exactly. So this is do you agree? And this you can call A tilde, and this you can call B tilde in the new coordinates. In the new coordinates. And then y is C T inverse Z, and this is C. Okay. Okay. Now, when you do Laplace and you do the transfer function or the transfer matrix, okay? So the transfer matrix for the tilde guy is C tilde, Si minus A tilde, B tilde, okay? D is never changing because D is not related to X, okay? So this is what? C T inverse, Si minus Ta T inverse, all of it inverse, TB. True? This is inverse. Now, the T and T inverse come out of this bracket, of this inverse bracket being inversed themselves. And this is also T inverse. Identity is T inverse, true? So this is actually C Si minus A inverse B. So the transfer matrix is not changed by coordinate transformations. The transfer matrix is not changing due to coordinate transformations. Okay? So that's why we can apply these coordinate transformations as infinitely many times as possible to write the ABC matrices in a form which is suitable to our analysis. Is this clear to you?
Yes.
Okay. So we are going to make use of this, you know. We are definitely going to use this coordinate transformations. So now this is explained formally here. Two linear systems, A, B, C, and A tilde, B tilde, C tilde, D tilde, having the same number of inputs and outputs and the same dimension of the state vector. So number of outputs P is equal to P tilde. Number of inputs M is equal to M tilde. Number of states N is equal to N tilde are called state space equivalent if there exists a non-singular or an invertible transformation matrix T such that A tilde is TAT inverse, like I showed you, B tilde is TB, C tilde is CT inverse, and D is not changing. Okay? So this matrix T is actually a change of state variables. We mix up state variables in such a form so the ABC are suitable to us. And we'll see the power of these coordinate transformations when we talk about structural properties of ABCD matrices. Okay? And now we have an important result. Two state space equivalent systems with equivalent initial conditions having the same input have the same trajectories equivalent through T and identical outputs. So in input-output, nothing is changing when you apply a coordinate transformation. It's all the same. Only the shape of the coordinates of ABC matrices changes. Two dynamical systems A, B, C, D, and A tilde, B tilde, C tilde, D tilde are called input-output equivalent if they have the same transfer function. So they are input-output equivalent if T tilde is equal to T. Okay. And now we have two remarks. Two input-output equivalent systems have the same number of inputs and outputs. However, it's possible to be realized, both of them, with linear systems, with linear dynamical systems, which have different number of states. So two input-output equivalent systems are not necessarily state space equivalent. That's what we are saying. So we have two notions, state space equivalent and input-output equivalent. Okay. For two input-output equivalent systems, we only have automatically this. D equals D tilde. That's the only property you have. Usually D is transfer function of infinity, is the value of the transfer function at infinity. Just keep this in mind. Now let's make a connection between state and input-output equivalence. There is a connection between these two. And the powerful result says that in this proposition says that two state space equivalent systems are always input-output equivalent. We just proved that, and you can see the proof once again more detailed on this slide. So T tilde is C tilde Si minus A tilde inverse B plus whatever. So this is CT inverse. You see all the calculations, and now here it's explicitly we show, yeah, because we know that identity is T inverse. Okay. Identity is T inverse. We can factorize T and T inverse in this fashion, and we recover the original transfer function. Okay. Of course, the converse is not true. Okay, we just said that. Okay, so state space is always input-output equivalent. However, conversely, an input-output equivalent does not necessarily mean that it's state space equivalent, because again, we can have different state dimensions, systems of different state dimensions realizing the same transfer function. Okay. Note that the notion of input-output equivalence is based on the transfer matrix, so it's based on input-output behavior, whereas the notion of state space equivalence is based on the state, so this is related to the internal behavior of the system. Okay. For any transfer function matrix, there are infinitely many state space realization. So for a transfer function, we can write an infinity of matrices A, B, C, and D due to the state space equivalence. Okay. And this is very, very interesting and very important. Okay. The problem of the dimension of the state space realization is essential. So to start with, before going towards approximating dynamical systems with lower dimensional systems, it's relevant to discuss first the so-called problem of a minimal realization, or the minimal dimension of a state space realization for a given transfer matrix. Okay. Note that minimal dimension does not mean approximation. So this is purely exact. However, approximation is going even further, is trying to approximate with a dimension which is lower than the minimal computed, exactly computed dimension of a state space realization. Okay. So for the minimal dimension of the state space realization, we get the so-called minimal realization. Okay. Strongly connected to the structural properties of the systems. From now on, so part of the ingredients we are going to learn in these lectures about state space systems, part of them are going to be very useful for one model reduction technique, and the other part of properties is more essential or more relevant for another model reduction technique. You'll see. Okay. One of the crucial properties of state space systems, or of systems in general, is the property of stability. I showed you that when I was discussing the pendulum. Okay. The hanging equilibrium, the zero equilibrium of the pendulum, induces the idea of stability because the system is always returning to that type of behavior. Okay. Whereas the behavior of the pendulum raised pendulum, the pendulum upside down, is unstable, because the minute you disturb that position, the system is never going to return to that position. Okay, so I'm going back to my pendulum. So this position is stable because no matter how I make a perturbation, okay, the pendulum is always coming back. You agree, right? Is always coming back, right?
Yes.
So this is stable. Whereas in this position, any perturbation is sending the pendulum out of this position. It's never coming back. It's never coming back. Okay, so this is unstable. Unstable. So we need to formalize that. Stability is investigated in this ABCD framework with respect to the behavior of the state x of t, so of the time evolution of the state. And this is called Lyapunov, or internal stability. Okay. We are used to discussing about input-output stability. You did that from the signal and systems course. I'm talking to the control engineers. Okay. Control engineers have been studying stability from an input-output perspective throughout their entire bachelor studies. Is this correct? I think this is a correct statement, isn't it? Can you confirm that?
Yes.
So mainly you have been with at control engineering when you studied the PID, later at industrial plant control. in the 4th year also. And all the entire spectrum of courses and studies you have been doing throughout your bachelor studies was talking about input-output stability. In this lecture, we are interested in internal stability of the dynamics. Okay. So internal stability, Lyapunov or free stability. We call it free because the stability, internal stability, is not depending on the input at all. The input in the discussion of internal stability is totally irrelevant. Okay. So the behavior of the state is with respect to the homogeneous equation x dot is ax. I remind you that for the x dot equals ax, the solution x of t is x0 times, no, sorry, not x0, x0 is not in front, x0 is in the, is exponential of at times x0. Now, what happens to the time evolution of this formula? Of course, you probably, your intuition is telling you that a system is stable if the state vector x of t is going to what? When t goes to infinity. Where should x of t go for a system to be internally stable? What should be x of t when t equals to infinity for a system to be stable? What's your intuition telling you?
To x0.
Not really, because it can't necessarily go to the initial condition.
To 0?
To 0, exactly. Because you do not want dynamics. If you do not want dynamics, x should go to 0. Okay? Not necessarily a constant. A constant should also be enough. But this is a fine discussion we're not going to get into. But when the stability is asymptotic, it should go to 0. When stability is not asymptotic, it should go to some constant value. Very good. So now we give the definition, the general definition of internal stability of a state space system with dynamics. A dynamical system is called internally stable if for any positive small epsilon, there exists a delta depending on this epsilon such that width should be here. Width. Okay. We have that the behavior is restricted, the time evolution for at any moment of time is restricted by this epsilon. Okay. So this is the general definition, the epsilon definition of the stability. As we all know from mathematics, of course, the definition with epsilon is useless from a practical point of view. So probably we'll need we'll need ourselves to go to a practical criterion or practical criteria, both theoretically and numerically. Okay, we also need a numerical criterion to study the stability of a dynamical phenomenon. A stronger notion, and more important essentially, and also quite very, or the most important in control, is the so-called asymptotic stability. So a dynamical system is called asymptotically stable if for any initial condition, this condition, so t of infinity goes to 0, x of infinity goes to 0. Okay, this is called asymptotic stability. Asymptotic stability. Of course, these are also related to the internal energy of a system. These notions are related to internal energy as well. However, we are not discussing very much this internal energy or Lyapunov way of thinking. You will see this notion if you stick to the second year of this master. There is a nonlinear control course in the second year who is going to explain the nonlinear, the Lyapunov way of thinking of stability of equilibrium points. Okay, so you'll see more details about energy and internal stability next year. Okay, no, next semester, sorry. In the next semester, okay? We'll discuss more about that. But for the time being, for this class of dynamical linear systems, it's enough to understand that asymptotic stability means only means that the state vector or the state evolution, the free evolution of the state, is going to zero asymptotically as time flows to infinity. Now, the definitions are quite general, they say here, being also used in the case of nonlinear systems. Actually, the linear discussion is a particular case of the nonlinear systems. This is clear. In the linear case, there are some simple consequences because we have this specific structure of the solution, which is not to be found in the nonlinear systems case. We have this simple solution with the matrix exponential. Okay, so the condition of the definition has a simple consequence that the system is internally asymptotically well, internally asymptotic stable, whatever. If and only if the transition matrix, which is E, I remind you that phi is E to the power AT, so this is phi of t x0. Okay, x0 is a constant. The system is internally asymptotically stable if and only if the transition matrix is asymptotically zero, okay, when t goes to infinity. Okay. Of course, this is also quite a large definition, and this is also hard to apply in this fashion. We need a more practical criterion. We need a more practical criterion. Since phi of t is the exponential of the matrix AT, it's only relevant, or it's only fair and natural to discuss the way how we compute this matrix exponential, because this is the key towards understanding stability. This is the key towards truly understanding the stability of a linear dynamical system. Okay. Right. Now, to compute the matrix exponential, we need to make use of the Jordan form of a matrix. Okay, because we need to use its diagonal elements. So probably definitely the computation of the matrix exponential is bijectively, if you like, related to the computation of the Jordan form of the matrix. Okay, because the matrix exponential is satisfying this property. E to the power AT is E to the power, so a matrix A always, which has eigenvalues, always admits a decomposition of this form, a coordinate transformation, where G is the Jordan matrix associated to the matrix A, okay, where the eigenvalues are in blocks if they have more multiplicities, or themselves if they are all distinct, on the diagonal of the matrix. Okay, and we have this property. And the funny thing is that for the matrix function, the coordinate transformation is jumping from the exponent, from the power, is jumping in front and at the back of the matrix, and then you can compute the diagonal of such a matrix. So the exponential, this one, is taking this form. We are not going to use this computation for exercises for that matter, but the theory here is important to understand the practical criterion, or the more practical criterion, theoretical criterion, we are going to give for the stability of a dynamical system. Okay? Okay. For this reason, you need to recall yourselves characteristic and minimal polynomial, Jordan canonical form, eigenvalues, and multiplicity of the eigenvalues. Okay, multiplicity of the eigenvalues. Okay, so yeah, if you I just remind you that if you have a matrix, a square matrix, okay, the minimal polynomial, the characteristic polynomial, minimum characteristic if the matrix is non-derogatory, is pretty much the same. Okay, is that lambda I determinant lambda I minus a. Okay, and the roots, yeah, the roots of PA lambda are the eigenvalues of the matrix A, the spectrum of the matrix A. Okay. Now these roots can be simple, lambda 1, lambda 2, distinct. Simple means distinct. Lambda 1, lambda 2, lambda n. Or they can have multiplicity. They can be multiple. Okay. So you can have lambda 1, lambda 1, lambda 2, and so on. Okay. Simple eigenvalues and multiple eigenvalues, or multiplicity 1 and other type, and multiplicity higher than 1. Okay. These Jordan blocks, so if you have multiplicity 1, then the matrix exponential is T inverse is this guy. Now, if you have multiplicity, okay, then e to the power at is T inverse e diagonal. I would say it like this. Let me make it more compact. T inverse diagonal of e to the power j I t, where j I is associated, yeah, is the Jordan block of eigenvalue lambda I of multiplicity, okay, ji of multiplicity ji, and ji is this one, lambda I, 1, 1, and the rest 0. Okay, and here is a 0. This is the Jordan block associated with a multiple eigenvalue lambda I, and this is of dimension ji times ji. Okay, it's not R, it's actually C, because they can be complex. Okay. Okay. This is a quick reminder of linear algebra. Okay. You can find all of these details, and you can recall all of these details in the book of Antulas, which is on Moodle. If you really want to recall these things. So we can see that the phi of t, because this is phi t, no, this is phi of t. This is highly related to the eigenvalues of the matrix A. It's essentially computed based on the eigenvalues of the matrix A. So probably A is going to phi of t is going to 0 if the eigenvalues suffer some property. Let me just remind you another fact. Okay. So lambda I is a complex number, true? Which means that lambda I can be written as sigma I plus j omega I. Okay, j is j squared is -1. Okay. All right. So this is a complex number. Okay. Now, exponential of lambda I t is exponential of sigma I plus j omega I times t. Agreed? This is further e to the power sigma I t times e to the power j omega I t. Okay? Now, when t goes to infinity, where is this going? That's the question. Where is this going when t goes to infinity?
Infinity.
Not necessarily. Not necessarily. We have two terms here, okay? We have two terms, so we need to investigate the behavior of each term at infinity. Okay? Let's first investigate the complex term. Now, e to the power j omega I t, I remind you from complex numbers, is cosine omega I t plus j sine omega I t. Okay? So, the limit of when t goes to infinity of the exponential of j omega I t is what? We don't know what the limit is because we cannot compute it, but the sine and the cosine are bounded, okay? So essentially, we don't know what the limit is, we only know that it's finite. True?
Yes.
It's finite, that's all we know, fine. Now, e to the power sigma I t. This is real number, yeah? Sigma I is a real number. Okay? Then limit when t goes to infinity from e to the power sigma I t is, of course, we have to discuss the cases. Sigma I larger than 0, sigma I equals 0, and sigma I negative. So sigma I positive, 0, negative. Do you agree? Is it true? You cannot discuss the exponential just like that. So what is the limit when sigma I is positive?
Infinity.
Infinity. What is the limit when sigma I is 0?
It cannot be determined.
No,
We must.
it's a constant. It's 1.
Oh yeah, it's an exponential.
And when sigma I is negative,
0.
0 exactly. And probably this is the case which is relevant for. This is important for stability. Okay. And now look at the stability criterion. Look at the stability criterion. Okay. The dynamical system A, B, C, D is internally asymptotic stable if and only if the spectrum of A, so the eigenvalues of the matrix A are all in the left half complex plane. So that means if and only if, how is sigma I? If and only if sigma I is what? Positive, negative, or 0?
Negative.
Negative, exactly. Negative. The dynamical system is internally stable if and only if, okay, sigma, so this is equivalent to sigma I less than or equal to 0. Less than or equal to 0. So stability, as we want it, as we like it, as we're interested in, should be with sigma I Negative. Do you agree? Do you agree?
Yes.
Yes. So this is stability. And we'll see that even when we do model reduction, when we perform approximation, the main goal for the approximating model is to preserve stability. Stability is crucial, is central. Okay? Stability is central. We need to preserve stability when we do model reduction. Yeah, so just remember, I'm going to write it here. Model order reduction must preserve stability, the stability of the original system. Okay, if the original system was stable. Okay, so this is how you assess stability from a theoretical point of view. Of course, you also need a more practical numerical criterion to assess stability. Stability cannot be assessed in MATLAB by only computing eigenvalues. I mean, okay, for low dimensional systems, okay, for the pendulum or the card pendulum, or even for the CD player or your building, MATLAB is able to compute 50 eigenvalues, and you can inspect visually. You can just look at the 50 eigenvalues, and you can assess stability. But this is not practical. In practice, when you have a huge system, a power system, you saw the example of the power system in the introduction to this lecture. That's not feasible. That cannot be done visually inspecting or looking at the eigenvalues because you cannot compute millions of eigenvalues. So you need a more practical criterion to numerically assess the stability of a dynamical system of the matrix A. And this is given by some nice reasoning from the nonlinear systems, which we are not going to get into detail. We are only going to present the linear version of the nonlinear theory that's lying behind the following slide. So stability can be related to a Lyapunov matrix equation. Okay. The equation A transpose P plus PA plus Q equal to 0 with a square matrix A and a square matrix Q in the unknown given by the matrix P, which is also an n by n square matrix, it's called the matrix algebraic continuous times, or simply the Lyapunov equation. This is called the Lyapunov equation. Have you encountered Lyapunov equations in your studies before?
Of course.
Of course. The economic studies, have they seen the matrix equations before? I'm asking our mate here, who has economic background.
Yes.
Have you seen matrix equations before, such as Sylvester or Lyapunov equations?
No, I don't recall. Right.
Okay, I'm sorry about that. Maybe you'll read in the book that is uploaded on Moodle, and you can also Google Lyapunov matrix equation. I'm just giving you the flavor of it, okay? And maybe your colleagues will show you how to use it. I'm telling you here how to use it for stability, okay? So
yes.
Yeah, let me make a short introduction to you. So a matrix equation, you know, an equation, an algebraic equation, is a scalar thing, a polynomial equation, okay? We are talking about polynomial here, okay? Ax plus b equal to 0. Okay, this is an equation. We understand this, okay? Or ax squared plus bx plus c equal to 0. We understand this, okay? Now, if you substitute x with a matrix, you can have ax plus b, also an equation, but x is a vector or a matrix, and here you need to have dimensions. So for this object, you need to have proper dimensions. Okay. This matrix here, the Lyapunov matrix, that the Lyapunov equation that I just showed here, this is linear in P because it's the P matrix appears only at power 1. Okay, so this is a linear matrix equation. Okay, this is a linear matrix equation. Okay, it looks like AX plus B equal to 0, but it's a bit more than that. It's a bit more than AX plus B because you also have the symmetric term A transpose B. Okay. Okay. But this is a matrix equation and it can be solved. It can be solved numerically. MATLAB knows about Lyapunov equations, and the command is liap. Liap. Okay. This is the command to solve Lyapunov equations in MATLAB. Okay. So this is a matrix algebraic linear equation in the unknown P. Now, the question is, how is this related to the stability of a system or the stability of the matrix A? How is this related? Okay. How is this related? And this is a theorem that says that if A is asymptotic, so first we start with a necessary condition. Okay. So if A is asymptotically stable, that is the spectrum of A is in the open left half plane, then the Lyapunov equation has a unique solution P, which has an explicit formula. Which is this one. Okay. So you can compute it explicitly. Of course, this is done by hand. You do not do this in MATLAB. Okay. This type of matrices in this form with this integral, they are called infinite time or infinite horizon Gramians. We are going to use this further, Gramian. Okay. All right. So we also have a short proof here. Okay. If A is asymptotically stable, then this 7 is well defined. Okay. Because Y is well defined, because the exponential here, these exponentials, when P goes to infinity, when time goes to infinity, sorry, they go to 0. Okay. So if A is stable, if and only if EAT goes to 0 when T goes to infinity. Okay. we just talked about that. Okay. This is not important. Okay. We just talked about that. Okay. So that means that when you have here the integral to infinity, it's no problem. And now, what do you mean that P in this form is a solution of an equation? Well, if P is the solution of the equation, then P should verify the equation. Do you agree? This is how you prove that P is a solution to the equation. You just plug it in the equation and compute. So plugging in A transpose P plus PA, the matrix P in 7, and doing some simple computations, and also noting that you have some derivative here, you end up with this. Now, this is e to the power A transpose T Q EAT at infinity. How much is this point? How is this at infinity? What is the value at infinity of this function? A is stable, asymptotically stable. So what is the value of this function at infinity? The value of this function at infinity, Q is a constant matrix, and A is an asymptotically stable matrix.
Is 0 minus...
It's 0. Minus E to AT is 0, which is 1. So minus Q.
Yes.
Okay. So this is minus Q. Fine. So indeed, P is the solution of the Lyapunov equation. Now, of course, we also need to prove that this is unique. Okay, I'm not going to get into details. You can build up a linear application, so on and so forth, surjective, bijective, whatever. So essentially, this function, you prove that this linear matrix function, okay, so this is a function of a matrix, okay? This matrix function is bijective, just like in the classic scalar case, ax plus b, yeah, the linear function is bijective, okay? So you need to prove that. I'm not going to get into details. So P in 7, if A is asymptotically stable, P in 7 is the unique solution of 6. So how is this helpful in me assessing the stability of the matrix A? This is the question. Okay. Now we have some remarks. If Q is symmetric, okay, so this means that the matrix Q is symmetric, okay? Then from 7, automatically, also this matrix is symmetric. So P is symmetric if Q is symmetric, because since P is actually defined by Q. Okay. Now, if Q is semi-positive definite, then also the solution P is semi-positive definite. Furthermore, if Q is positive definite, then the solution P is also positive definite. Okay. Okay, so this theory, they say here, is used especially in nonlinear system for testing stability. This is true. So this is how you assess the stability in nonlinear systems. In the linear case, however, we have a more practical numerical result as a consequence of the nonlinear result of the nonlinear theory. And we have the so-called Lyapunov theorem. Okay, and this is the sufficient condition. And this is the practical numerical test. This is the practical numerical test for the stability of the matrix A. Assume there exists a symmetric matrix P, a symmetric and positive definite matrix P and Q, such that P is the solution of the Lyapunov equation A transpose P plus PA plus Q equals 0. So assume to reformulate equivalently, assume that the Lyapunov matrix equation A transpose P plus PA plus Q equals 0 has a positive definite solution. Then the matrix A is asymptotically stable. Yeah? A is asymptotically stable. A is asymptotically stable. Okay. Yeah. So this is a way you can test whether your system is stable or not. Okay. Okay, you have a proof here. There is a. Can you see my screen? Something. Okay.
Yes.
There is a proof here. I'm not going to get into the details of the proof. Okay. I'm going to get into the details, but I'm going to get to the how this is how is this result how can this result be used in practice? Okay, this is the question we are addressing now, and maybe next we can do some exercise in MATLAB, so we can actually see that this really works exactly on the example that we showed earlier of the pendulum. We can look at, and you can work it yourselves at home on the card pendulum, card controlled by a double pendulum, on the CD player, and on the building example. Okay. So in the above theorem, if we assume that P is positive definite and Q is positive definite, then A is asymptotically stable. Okay. Oh yeah. So okay, then A is asymptotically stable. Numerically, you can find tests. There exist tests to test the semi-positivity of the Lyapunov solution. So you can use Lyapunov solvers and check whether the solution is positive definite or not. Okay. It says here that the Lyapunov equation can be used for testing the stability of a dynamical system, solving a linear system of equations, a considerably simpler problem compared to the computation of the spectrum of the matrix A. That's why we use this Lyapunov equation to assess the stability of a linear system. Okay, let's go back to the MATLAB. I'm going to share the screen on the other computer, and let's play with it and see what happens. Okay. Can you see the other screen, please?
Yes.
Okay. Let's just take the matrix Q equal to the identity. Yeah. So take Q equal to C because already C is the identity matrix. Okay. And let's do Liap of A. Let's see if this is the correct. If this is the correct syntax. Oh yeah, it is. It is the correct syntax. Okay. Yeah, and so this is the solution. We should call this P. We ought to call this solution here P. Okay. Okay. So F5. Okay. Okay. Now, what is a I'm not sure if you remember. Now I think I'm going to switch to the other screen once again because I need to remind you something. Do you remember what a positive definite or semi-positive definite matrix is? Hmm?
One thing was that its eigenvalues are positive.
Okay, but that's a consequence. What's the definition? That's a property. What is the definition?
X transpose
Exactly, very good.
of
A matrix
A.
A is positive definite if and only if if and only if X transpose AX is positive. This is a number for all X in Rn, X non-zero. Okay, so A is Rn times n. X is also Rn. Okay, so a matrix is positive, and here we can also put the semi-positive definite as well. Okay. Okay. If and only this is the definition. Now the consequence, the property, is indeed A is positive definite or semi-positive definite if and only if lambda I are all positive definite for all lambda I in the spectrum of A, I equal 1 through n. Okay? Exactly what you said. Okay? So this is positive definite, and same goes for negative definite. Yeah, okay, so A is negative definite. It's the same, okay? There is no difference. Okay. Now, how to assess this? So you can do this. I'm not sure whether there exists, there must be in MATLAB positivity tests of a matrix. Okay, we should look it up. If you ask me right now, I'm not thinking. So the only thing I can think about here is to take X equals, I don't know, 10.
Teacher, you didn't share the
Oh,
MATLAB.
now I need to share the MATLAB. Sorry. I need to reshare the MATLAB. Okay. One second, please. Okay. Can you see the MATLAB now?
Yes.
Fine. Now you just take an X and you make X, but this is not relevant, okay? P X. Oh, no, this is wrong because I should have done it. This is a line and the other one is a column. You see? It's a positive number, right? Let's take with negative numbers. Okay. You see? Again, a positive number. Okay. So P is indeed positive definite. So A, by the result we just gave, A is indeed A is indeed a stable matrix. Okay. No, there is nothing. Let's try to. I'm very curious. I haven't thought about it. Let's do some research together and look up a positivity test for a matrix in MATLAB. There have to be efficient algorithms, probably based on some sort of optimization, to search whether a matrix is positive definite or not. Do you know of anything of this sort? Have you encountered such things? I'm asking the control engineers now. Some efficient test to test the positive definiteness of some matrix.
I searched now and it looks like KHOL function can help
That's
us.
the Koleski factor. Okay. But I'm asking you from your experience, not to look it up right now. From your experience.
I only used the eigenvalues.
Oh, you only use the EIG. Okay. Symmetric. Look, let's see what MathWorks has to say about that. Call A. Okay. So the Koleski factor. Call A. Display. Catch me. Display.
That sounds like an exception test. I mean, I think if the program raises an exception, then the matrix is not.
So is this useful or not?
I think it is, but it might be hard to use.
Why?
Because of the way it is called in those 4 or 5 lines of code.
Why do you say that again? Why is it difficult to code? Because you just compute the Koleski factor. It cannot be extended also to check whether the matrix is symmetric because it's semi-definite. Yeah, so you only use this for positive definite, not semi-definite.
Yeah, I think it breaks when
Breaks, right. Numerical consideration is symmetric. But you can do something else. Look here. Well, it's less efficient to use egg. You see, it's less efficient to use egg. Look what it says, exactly what I told you. Yeah, and check the value. The method is more flexible since you can also use it to check whether the matrix is symmetrical. Still, for small matrices, the difference in computation. Okay. So the method requires that you use is symmetric. Oh, sorry, there exists is symmetric. Okay. Oh, but you still need to compute the eigenvalues, right? Huh? Look. You need to use this code, right? Oh, here is symmetric P. I'm interested. Egg P. You don't want to look at them. Tall. Let's use tall. Tall should be what? 0.0001, something like that, right?
Yeah,
Huh?
I agree. I agree.
Is
Or
semi
maybe some orders of magnitude higher. I don't know.
what do you mean? Should it get more here?
I think I used in MATLAB and even when I worked with tolerances 0.001.
Ah, 0 point. So, oh, you say it's enough to do it like this.
I think so.
Let's try. Okay, and also let's compute call P. I'm very curious how this works. It's the first time I'm doing it. I'm researching it live with you.
I remember I worked at a software which computed the stability of buildings and stuff like that, and
Yeah, you're going to have the building. Use it building.
It used a lot of approximations and modeling and stuff like that, and I remember the tolerance was 0.001.
Right. Look, it's working. It's working. I hate this TF. Why do you call it? Because it's misleading. I think it's transfer function. This is not true. This ain't no transfer function. Why do they call it TF? From what? Tolerance? No. Is symmetric P. F. Why do they call it TF? Let me just check. Now, what is this? Oh, sorry. I got a notification on Teams. I don't know what this is. Let me just easily check this. Oh, okay, fine. Oh, you replied something to us? Oh.
Yes, I found on forum, a MATLAB forum, this.
Rather than using, very good. Why didn't you say so? you can.
I just edit on.
No worries.
Teams.
So let's read what you have to say. So rather than using egg, because I don't want to use egg, it's more computational to use the call. Call provides a national signal output called P. Oh, which is 0. Wow, this is lovely. This is lovely. I like this. I like this code because I want to avoid using so you write it like this, if I'm correct. Boy, I love this master because I'm learning stuff together with you. I'm not using these things because I do nonlinear stuff, so I'm not very. But now I'm learning. I haven't used so much, or the MATLAB I'm using in my simulations is a bit different. Okay, and I'm using Maple actually. Oh, so what does P equal to 0 mean?
That is positive.
Oh, it's okay. Okay, can we make a nice code so we can display. Let's make something nice, okay? So you can consider this lab practice because we have 2 hours lectures and 2 hours lab practice. So how can we make, I want to make a simple code to display because I saw here. So where is it? Okay. Catch, what is this? Display and not display. What is this code with catch? What does it mean?
I think it's like an exception in C or in C++.
Oh, okay. No, I want to disp. Does this work in MATLAB? This function disp?
Yes, but I was talking about that catch only.
Oh, okay. Oh, okay.
I think that this will show something in the command line.
Equals to 0, like this, right? Else, is this correct? Check me.
Yes, I think so.
Else disp matrix is not. Okay. Let's see if this works. I'm curious.
And after if.
And true. And I'm getting old. I'm not writing so much code these days. At any rate, I wasn't good at software writing anyway. I don't know.
And p equals 0.
True.
It's
You see, I'm a geek. I have no idea about programming. If I had, I wouldn't be here today. I would be working in some big company. Sorry about that. Okay. You see what I mean? I'm a total wreck when it comes to software development. I barely know how to add A plus B in C or C++. It's always the pointer stuff and the I++ and stuff like that was killing me when I was studying. So I veered off from programming and did something else. But this is about me. Okay. So indeed, the matrix is positive definite. So indeed, the matrix is positive definite. Okay, and you can add, due to Lyapunov theory, you can add in this statement here, matrix P. Okay, matrix P is positive definite. Okay. Hence, because it's Lyapunov, hence A is asymptotically stable. Okay. And also determine if it's semi-positive definite. Huh? Do you know? So we can do it like this. Because we know we have the theory is on our side. The theory is on our side. Okay. So this is nice. Okay. So we can easily assess stability. Let's try to do the same. With a random matrix of larger dimension and see what happens. Do you agree?
yes.
No, how was that? A is rand. Is rand what? Oh, I always forget how to use this rand function. Rand. I want to build a square matrix of random numbers. Okay. This is what I want to do. And then check its stability. Okay. Using rand. Look, you see? Rand n. Okay. Okay. Let's start easily. Rand 10. Okay, and then let's use this code. let's use this code. Let's use this entire code. Okay. Now we extend what we have just seen in theory to this more general case. So Q is I10. Actually, no, I would do it like this. Let's call this N. Let's take N equal to 10. Okay. You agree? IN. P is this. Okay. And let's use this whole funny thing here. Okay. Agreed, right? Let's save this guy. Let's save this guy. Where was it? Here. This is here. And this is here. Lyapunov ability testing. Okay. Oh, shit. MATLAB hates dashes, but he likes this. Okay. Cool. Right, mates. Dot. First of all, let's indeed verify using the eigenvalues of P for the pendulum. Indeed, you see, the eigenvalues are positive. Okay. Now let's go back to the random matrix. Let's go back to the random matrix and run the code. See what happens. You see, it's not. Apparently, it's not. Why am I seeing the P matrix? Because I do not want to look at the P matrix. It shouldn't be open. So semicolon. Okay. Okay. Oh, tall. Should have here tall equals 0.001. Okay, let's go back. Is not symmetric positive definite. Okay. Does this P show you if it's semi-positive definite? No. You see, there are positive eigenvalues. Not positive. Right half plane eigenvalues, positive real parts. Okay. Okay. So let's go back. And I'm not sure whether we can ever find okay. Now let's move to 100, right? It's symmetric somehow. How the hell is this symmetric? Because it's got also non-zero imaginary parts. So this is symmetric, is not working properly, right? Do you agree? Can you hear me?
Yes.
Oh, okay. So,
but symmetry isn't a different property?
No, symmetric means that the spectrum is real. So the eigenvalues here should all be real. Okay. So it failed because it's not real. Okay. So with random is difficult. With random, it's difficult. Okay. Let's go back.
But we didn't see the result from call.
Col, yeah, col. From Koleski factors. That's what col means. The Koleski factor.
Yes.
Yeah, no, I was asking about asymmetric. You see, the asymmetric here is not working really properly, if you ask me. Okay.
But he displayed something after this this eigenvalue display.
Look, this
is okay.
Okay, so it says 1 here. It shouldn't be 1, huh? It should be 0. Or am I missing something?
No. In
You see, it should be 1 if the matrix is symmetric, but our matrix is not symmetric. So it's failing somehow.
Okay, but call.
Okay. Call is better.
Okay, this about it. I wanted to.
Yeah, call is better. No,
Okay.
I'm checking all the methods. I'm checking all the methods. Yeah, call is the best one if you ask me at this point. Okay, so let's try a 10,000 order matrix. I hope it's not cracking. It's not crashing. Right. Let's see how much. No, it's not using too much CPU. Strange. Okay. Let's wait and see. It's taking some time, but we're patient, right? Oh, sorry. No, I was wrong. MATLAB is right. P is symmetric. P is symmetric, but it's not positive. It's about P, not about A. Sorry. My mistake. It's about P, not about A. Okay? P, which is the solution of the Lyapunov equation. Okay? Now I'm right. I was wrong. Indeed, the P is symmetric, but it's not positive definite. The previous P. Okay? Is it clear?
Yes.
I don't know why it's taking so long, because it should be. It's taking long. Well, we've got enough time to wait. So, excuse me for a second. I'll be back in a second. Can you hear me? Huh? Can you people hear me?
Yes, we can.
Yeah, the problem is that the other guy has is locked. Yeah, I managed to crash it. So apparently this 10,000 thing was breaking it because it's a slow Windows-based computer. So let's go back to our to our the slides. But the idea, I think, is clear, right? You should try this at home on your more powerful computers, right? You see what I mean? Okay. Oh Jesus! How am I gonna get rid of this? Right. So can you see my screen now?
Yes.
Okay. So you see the slides now, right? Because the other one is completely jammed. I'm not sure how. I think I have to just reset it manually. But anyway, I'll take care of him later. Okay. So, but you get the big picture. Okay. So maybe you should try this yourselves at home. Probably your MATLABs are sitting on a more powerful computers. Okay. So try to test that. Take a random matrix of very large dimension, and check its positivity without computing the eigenvalues. Use the code we have just seen. Okay. So essentially, stability is a question related to the placement, to where the eigenvalues of a matrix are residing. Okay, so if they are here, the system is asymptotically stable. If they are on this side, then it's a big problem. Okay, because you're unstable. Also, another very interesting issue is what happens if your eigenvalues are sitting on the imaginary axis. This is a crucial property because the imaginary axis means oscillations, essentially. Okay, but for control, usually in control, we control systems to force the eigenvalues of a specific plant to sit in the open left half plane. This is the goal of control. Okay. Okay. Right. Now, another discussion we need to make.
Teacher?
Yes.
I'm sorry. About Lyapunov equation.
Yes, please.
Why P and Q matrices have to be positive defined in order to yes
Definite, not defined. Positive
define?
definite. Yes, because of the proof. Otherwise, this is not what happens here is not true. So assume. So if no, look at the result. If this and this is true, then this happens. Okay. So if I'm not proving it right now, I'm not giving you the proof here. Okay. The proof is I can send you the slides for the proof of this. Okay. All right.
Okay. Thank you.
But the idea is, so this essentially this looks like like an energy function. So the Lyapunov idea is like this. You have a dynamical system, okay? X dot, all right? X dot is AX plus BU, okay? Now, you take a function V of X to be X transposed PX, okay? Do you follow me?
Yes.
So this is a function. Now, assume P is positive definite. If P is positive definite, then V is positive definite, okay? So V is defined on Rn because X is in Rn, but the value is in R, is a scalar, okay? Also, V of 0 equals 0, okay? All right? Such a function is called a Lyapunov function. This is called a Lyapunov function associated with the system. This is because we are talking linear system, this is a quadratic function. Okay? In general, quadratic functions of a dynamical system mean energy. Do you agree?
Yes.
They mean energy, okay? So if you have, example, if you have a linear oscillator, okay? So x dot is x1 dot is x2, and x2 dot is minus a x1 minus b x2, okay? A and b positive, and b positive, okay? Then v of x can be, because this is position, so x1 is the position, okay? And x2 is the velocity, right? So what is the energy? What is the total energy of a mechanical oscillator? Is the kinetic energy, right? Okay, I don't have M here. I have, okay. All right. Plus
Okay.
the potential energy, okay? So this is kinetic energy. This is potential energy. True? Do you agree? So this is 1/2 x transposed x. P, how much is P here? If you look at this, P is the identity. You can also take half here. You should take half here. Sorry. Let me write this again. Okay? P is the identity. So V of x, the idea of Lyapunov function comes from energy. This is the total energy. Okay? Okay? So this function here is an energy-like function. It need not necessarily be the physical energy. So here, energy, this is more of a systemic concept in this case, okay? So this is not necessarily physical energy, okay? So this is not unique, by the way, not unique, okay? Energy is a relative concept, and it makes sense. It's what philosophy is. This is our life, okay? Energy is a relative concept, okay? So the energy in physics need not necessarily be the energy we look at. Do you follow me?
Yes. Mm-hmm.
Okay, so we have this P, which is positive definite. Now, energy, when is a system stable? When the energy, the variation of the energy, okay, when the variation of the energy, okay, is less than or equal to 0. Okay? Because if the V of x is 0, that means that V is constant. The energy is not growing up. Do you remember? Yeah, it's not blowing up, like we discussed at the single machine, at the synchronous machine example in the introduction lecture. Okay. So a system is internally stable if its internal energy is decreasing to 0 or a constant level. Okay. All right. Now, if V dot x is satisfies this condition, which is difficult, then V will go to 0 when t goes to infinity. Okay. So this is asymptotically stable.
Okay, this is related to asymptotic stability. Okay, this is related to asymptotic stability. So asymptotic stability means that the internal energy, as time goes by and the system is evolving, is zero. Do you follow me?
Okay.
Okay,
Yes.
fine. Now let's go back to our linear case. Okay, so what is V dot in the linear case? What is V dot in the linear case? V dot is d to dt x transpose px half. Okay, so this is x transpose dot px plus x transpose p x dot. Do you agree?
Yes.
Right. What is x dot? X dot is ax plus bu, right? So x dot transpose is x transpose a transpose plus u transpose b transpose. Okay, we take u0 because I'm interested in the matrix A. I'm not interested in the matrix C. Okay? Stability is about the matrix A. Agreed? It's about the matrix A. Right? Okay, so let's substitute. So it's x transposed A P plus x P A x transpose P A. Okay? Plus x transpose PA, okay? So this can be written x transpose A transpose P plus PA. Do you recognize the Lyapunov? Now, you want this to be negative definite, okay? This is what you want. This is your desire, okay? But you know that so you need A transpose P plus PA to be like this, right? A negative definite matrix. Agree? But this is difficult to assess. So it's easier to ask that the solution of this equation with Q positive definite be positive definite. Okay? All right? This is in a nutshell. Of course, this is not the whole rigorous proof. This is why you ask, why you have this result. If P is positive definite, okay, because A transpose P plus PA is minus Q, okay? So if Q is positive definite, then minus Q, how is minus Q? Negative definite, okay? So now do you understand the reasoning? If P is positive definite, then Q, the solution, this equation is negative definite, is positive definite. So minus Q is negative definite, and then you get your result. Okay?
Okay, thank you very much.
Is it a little bit clear? No.
Yes.
It's difficult because I actually need a whole lecture of nonlinear systems for you to understand what's going on in this result. But you'll see this next semester, in the next semester. Okay? I have the slides. If you're interested, I can send you the slides about this subject, and you can look at it. Okay? Or you can wait until the next semester to see the whole theory about these things. Okay? So I'm not giving any proof. Okay? because there is no reason.
But you
Okay.
actually gave me.
Sort of. It's a sketch. This is only a sketch. Okay, this is not the rigorous whole proof. Okay, this is just a sketch. But if you're interested in Lyapunov stability in general, you can look it up on Google, because there's billions of results and books and articles and papers on this subject. You can look at it and you can further understand. Okay, the whole way of thinking behind this this reasoning. Okay. All right. So, mates, we have been discussing for 2.5 hours. Okay. Do you need something else? Do you need something more? Is it clear what we have been discussing today? We've discussed the important and the crucial property of stability. Have you got any questions, please? Have you got any questions, please? Mm-hmm.
I have an administrative question. It's related to the fact how can we access your notebook? You said that we can access the notebook, but
You go into the class Teams. You go into Teams.
Oh, in Teams.
Yes, in Teams, in the class, just like I'm doing it here. Look, I'll show you. Look at the screen, please.
Yes.
Okay. Oh, shoot. This is a bug of this stupid Teams. Okay, so Teams. Let me just close a little bit and reopen them. Sorry about that. Can you still hear me now?
Yes.
I'm sorry about this whole. Okay.
No problem.
I'm not sure if the recording is still on. So, do you still see my screen?
Yeah, it's still on as far as I can see. On
The recording is on, but we cannot see the screen.
Okay. Right now?
Yes.
How
Right
about
now.
now? Okay, fine. So, look, this is our class. Okay.
Yes.
More. Okay, this is on an iPad, but on your Windows screen, probably you can see. This is in Romanian. You can see class notebook or bloc notes școlar in Romanian.
Oh,
Okay?
I understand. Yes.
And that's how you open and you access it. You can see it in real time.
Mm-hmm.
Okay?
Perfect.
Okay? You can see it in real time. Okay, fine.
Thank you.
One other thing, no problem. I was trying to show you on Moodle. That's why I was accessing Moodle. We have to start doing some assignments. Because I'm a nice guy and I'm Okay, do you want me to prepare an assignment for you for this week, or do you want us to start in the next week? So I have here a test and an assignment. Okay, do you see that? The assignments and the tests are going to be 50% of your final grade. Okay, just I'm reminding you that. Okay, so there is an assignment prepared for you in the week of the 29th to 4th of April. Do you want to shift it backwards to this week? Do you want to do an assignment this week or next week?
Next week, that
Okay.
certain week.
Next week, it's mandatory, so I'm not going to let you go without an assignment next week. So next week, I'm going to give you this assignment called Lab 1, okay? And with a deadline of a few days for you to solve it and to upload the solutions in MATLAB, and with the pictures of what you write with pen and paper, you upload it back on this Moodle in this assignment, okay? And then I'll grade you for this assignment, okay? Is this clear?
Yes.
Okay, so next week, prepare yourselves to start doing an assignment. The assignment will have a few days. I'm not unreasonable, okay? I'm not going to ask you to do it during the class, okay? You can do it afterwards. You'll get a few days with a deadline, okay? And you need to work out the assignments in MATLAB. Agreed?
Yes. What about that test?
The test, yeah. What about it?
I mean, in that week we will have a test too, alongside that assignment.
That's a short quiz. That's a short quiz. Yeah, you can. I'll open it for you after the lecture. Okay.
Okay.
The test is going to be short. I'll open it a few hours, only probably 1 hour or so, or even less. You do it, okay? So I'm going to let you know, and you do it at the end of the class. Okay? At the end of the lecture, I'm going to give you a quiz from what we have discussed until now. Okay? I'm going to check out the questions. If not, I'm going to give it in the next week, in the week after that. Okay?
Okay.
Okay, fine. Right. So I'm going to stop sharing the screen sharing. The call is going to be open until 8 o'clock as usual. So if you have questions, you can write on the chat or raise your hand or whatever, and I can respond to your questions. Okay. In my opinion, this the amount of information is enough for today. Okay.
Okay.
All right.
Good evening.
Okay. You have a nice evening and a good week, and I'll see you mates next week. Okay. So the call is still open. Okay.
Thank you.
very
See you
much.
next week.
Yeah,
Goodbye.
next week. Cheers.
Goodbye.
Cheers.